So yeah, I guess we've been hearing a lot about the Quantum PCP Theorem. I'm going to talk about something different, which is the Quantum PCP Conjecture. I don't know who calls it a theorem. So we've heard a lot. So this was a joke, right? I'm going to talk about the same thing that we've heard about in every single talk up to now. So it's unclear if there's anything new I can say. It's also completely unclear that I'm the best person to be saying things about this. So, I guess this hour will be devoted to saying again what we've said, but all in one place. So it might be helpful to put everyone on the same page. And it can also be a discussion. So feel free to interrupt, raise the same arguments and counter arguments that we've heard before again, or raise new ones. So here's the plan for the talk. So a significant part of the talk will be devoted to just stating the conjecture, trying to make it precise, and arguing about whether this is the correct statement of the PCP conjecture. It's what we want to be. Is it relevant? If it's relevant, why? In what regime is it relevant? So we'll discuss the parameters. And then the two other parts will be, so in the second part, I'll talk about some possible approaches. So this will sort of build a little bit upon Luca's talk and try to see, well, okay, suppose we try to prove this thing now, what can we do, and where do we run into trouble? And then the last part of the talk, if I have time, I'll discuss more serious obstructions to the conjecture, and the same kind that was already discussed in Aram's talk. So obstructions, strong obstructions that say, well, the conjecture might be true, but it cannot be true in that regime. That's the outline. So let me start. So one thing that has not been done before, so I'll do it here, is and I think is kind of interesting, is just try to remember where this conjecture comes from. Who made this conjecture in the first place? Why is it made? And that might help us understand what the meaning of it is. So let me go over a little bit of history for all I know. So we can go back to the statement of the local Hamiltonian problem itself. So even this I'm not too sure. So the citation I'm putting up is the book by Kitaev, Shen, and Viali, but then I've heard this introduction of local Hamiltonian attributed to Kitaev in a lecture at Hebrew University in '99. And then I saw in Zev's talk, it was '97. So I don't know if you know better.
I got that from Umesh.
You got that from Umesh. Umesh, right. Maybe you're more qualified to say where this local Hamiltonian comes from.
I'm not sure where the date comes from. So it could well be '99. All I know is that it was conceived on, Kitaev conceived of it a few days before he flew to the Hebrew University to give a talk, and he wanted to have something interesting to talk about.
Okay. So then that's probably Kitaev, and it's probably in '99, because the '99 I got from Dorit, so it might be '99. So we've seen this problem a lot, but I'll just state it again, because maybe not everyone was in every single talk. So what's the local Hamiltonian? So right, Umar said, so it was introduced as a generalization of classical constraint satisfaction problems, right? That was the motivation. Find an interesting quantum generalization of something that's interesting classically, like local CSVs, presets. And so here's the statement. You have local Hamiltonians, Hj. So each of these local Hamiltonians is a Hermitian matrix. It has size d to the k by d to the k. So there's two important parameters. D is the dimension of each of the particles. For the whole talk, you can think of d equals 2 if you want, but it could be a little bit bigger. Usually we think of it as a constant. K is the locality. It's the number of qubits on which each of the Hamiltonians act. So these matrices act on k particles of dimension d each. So they're d to the k by d to the k matrices. Usually we tensor them with the identity on the other qubits to make them n to the k by, d to the n by d to the n matrices. And they have norm at most 1, let's say. Okay, so that's the input. And the parameter that we're interested in is the ground energy, or the minimum eigenvalue of the local Hamiltonian. So H here is just the sum of the local Hamiltonians. So there's the ground energy, and then there's the ground state, which is the eigenvector that's associated to the minimum eigenvalue. So that's the local Hamiltonian. And what's the, okay, sorry, I have a little picture. These are your qubits, and you can think of each Hamiltonian Hi on acting on a small subset of the qubits. So in that case, k is equal to 3, because each of the local Hamiltonians acts on 3 qubits. Local Hamiltonian problem is the following. Given an instance of this problem and two parameters a and b that are separated by an inverse polynomial, at least, is the ground state energy of the Hamiltonian at most a, or is it larger than b? So that's how Kitaev introduced the local Hamiltonian problem. We've seen this before. I think this is clear for everyone. All right. I'm going to give you examples, kind of trivial examples. I'll try to do this quick. It doesn't really matter, but just to make it a little bit concrete. One example is, just to remind you that this local Hamiltonian problem contains classical constraint satisfaction problems. So you can phrase, for instance, max cut as an instance of this problem. In that case, locality will be 2, dimension will be 2, and the constraints, these Hamiltonians, they enforce that qubits that are adjacent should be assigned different values. So if you really want to see what the matrix is, it would look something like this. It's something that assigns a score of 1 to the state 0, 0, and a score of 1 to the state 1, 1. So when the values, sorry, I did it the wrong way around. It should be the opposite of this. No, it's this, because you want to minimize the value. So you score -1 for when the qubits are 0, 1 or 1, 0, right? So this gives you a score of -1 when the values are different and you're trying to minimize the energy. This is the same as finding the largest possible cut. This you can generalize. So in statistical physics, you look at the Ising model, which you can think of as a generalization of max cut where you allow weights on the edges. I'm not insisting on this. And an example of a quantum Hamiltonian that generalizes max cut is the Heisenberg model, where again, locality k is 2, dimension d is 2. So there are qubits, but now you have a certain graph with edges, there's weights on the edges, and the constraints, instead of simply seeing that the 2 qubits should be assigned different values, they'll force the joint state of the 2 qubits to lie in the antisymmetric subspace. So this is basically saying that across every edge, you want the 2 qubits to be in a particular entangled state. That's the constraint. And it was shown recently that even for a very simple such instance of local Hamiltonian problem, k is 2, dimension is 2, Hamiltonians, they all look like this. The only thing that varies is the graph and the weights. Then this problem is QMA hard. But I'm getting a little bit ahead of myself with these examples. So let's go back to this, right? So what Kitaev and co-authors showed is that if the locality is 5, each constraint acts on 5 qubits, and they're qubits, then this local Hamiltonian problem is QMA complete. So there's 2 parts to showing QMA completeness. You have to check that the problem is inside QMA, and then you have to show a reduction from any QMA complete problem to local Hamiltonian. So showing that this is inside QMA is easy. The witness will just be the ground state of the local Hamiltonian. And then the verification procedure will be, well, you pick a constraint at random and you implement a measurement that is going to have a success probability that's proportional to the energy of the state with respect to the constraint. Not going into details, it's pretty straightforward. The other side is very interesting, showing that arbitrary QMA complete problem, for instance, circuit SAT. So you're given a quantum circuit, and you want to decide, does there exist a state that is accepted by this circuit, or does there not exist any state that's accepted by the circuit, right? That's just the basic QMA complete problem. And now what you want to do is take your circuit and construct a local Hamiltonian out of it, such that if the circuit had an accepting input, the local Hamiltonian has low energy, and if the circuit rejected all inputs, then the Hamiltonian does not have low energy. All the states have energy above this threshold B. And that's non-trivial. So, this is already done classically when you prove the NP completeness of 3-SAT. You take your circuit and you encode the circuit in a certain way by basically thinking of the circuit as a layered thing that acts on the input, and the witness will be will sort of represent the whole evolution of the circuit. So for every gate, you'll have new variables, etc. Maybe a lot of you have seen this. Quantum case, this doesn't work so easily because you can't copy the quantum information. You can't really deal with the different quantum states at different stages of the circuit. So the big insight that Kitaev had was to look at the witness here will be a superposition of the state of the circuit at all possible time steps. And then he showed that if this is how you think about the witness, then you can verify that a given state is in this form, just by making local checks, just by using local Hamiltonians. All right. So this was the initial result, and then there were a lot of improvements trying to, keep QMA hardness, so the same hardness, but for simpler and simpler instances of local Hamiltonians. So for instance, getting the locality down from 5 down to 2. This was achieved by Kitaev, Kempe, and Regev. And then more recently, there were further results. I think Daniel talked about this in his talk already, that try to get QMA hardness for physically relevant systems. So you start talking about what the actual local Hamiltonians look like, what the interaction graph looks like. So there's Oliveira and Terhal. They showed QMA hardness for a local Hamiltonian problem where the interactions are nearest neighbors on a 2D grid. And then this was improved further to systems that are one-dimensional, even systems that have translation invariance. So we're getting very close to proving QMA hardness for systems that sort of physically relevant. For instance, this Heisenberg model that I had in the previous slide. All right. So that's for the local Hamiltonian problem. So now we're interested in a particular version of that problem. So the quantum PCP conjecture. So I tried to trace back where this comes from. Where is it first mentioned, and what's a little bit the history of the problem. So the first mention I could find, that Dorit could find, I guess. I don't know if this is the first, but it's in 2002. It's some lectures that Dorit Aharonov was giving at the Hebrew University on quantum computing. And at the end of the lectures, there's a whole lot of open questions. And the last open question is, this is exactly what's written there. There's no more, no explanations. So there's a quantum analog of the PCP theorem hold. So that appears there. And then I don't know what happens afterwards, but further mention that you can find is on the blog. This is Scott Harrison's blog. He had an entry in 2006, so he was a postdoc at IQC at the time, and he calls it Quantum PCP Manifesto. And here's his statement of the Quantum PCP conjecture. You can read it. I guess I'm going to give a statement later, which is equivalent to what he's stating. Although, one interesting thing is that he's already pointing to an interesting difference between classical constraint satisfaction problems and this quantum constraint satisfaction problem, local Hamiltonian, which is that in the classical case, you have all these constraints, and then you're trying to find an assignment which satisfies the most possible number of constraints. And when you have an assignment and a constraint, the constraint is either satisfied or not satisfied. In the quantum case, you can see this here. There's one more thing that happens, which is that the constraints, there's these Hamiltonians that have a certain energy with respect to the state. They can be a little bit satisfied or very satisfied. So for instance, you can look at assignments which satisfy all the constraints a little bit, or things like that. So that's why he has these two parameters, epsilon and delta here. But I'll state an equivalent version of the conjecture soon. So this blog entry, he makes a few conjectures or predictions that are interesting. So first, he's 99% sure that the theorem, or well, conjecture, as I stated it for my talk, is true. Okay, so we don't know. 95% sure that the proof will be interesting. 85% sure that the proof is achievable in a year or so, and this was 2006. So 75% sure that the proof will be very interesting, and 0.1% sure that he can prove it. So at least this has been verified, but I don't know, not that he tried much. I don't know. Not that anyone else has been able to prove it either. So. And okay, another interesting thing, this is an interesting blog post. It's strange to go back to 2006. And there's some comments, and there's few comments. There's like a dozen comments, and they're all very pointed, very interesting comments, very relevant now. In particular, there's one comment I wanted to show you. I don't know, Luca, if you remember writing this comment on Scott's blog. It's interesting. It's a very good comment, and I'm going to go into that comment a lot during the talk. So you should focus on the last paragraph. And what Luca is pointing out is that here, when we're introducing this quantum PCP conjecture, we're saying, well, look, I mean, there's constraint satisfaction problems, and there's the classical PCP theorem, and this has been so exciting. Why don't we define a quantum version of it, and then study the quantum version, right? Surely it'll be exciting. And Luca is saying, you have to be careful, because it's not at all clear that the most productive, results, theorems, conjectures in quantum information will be obtained simply by taking things that are known classically and saying, well, let's make a quantum version of it. And for all that I could see, up to that point, this is what was happening. This was the main motivation for the Quantum PCP, this Quantum PCP manifesto. And if you look at the other comments in the blog, people are pointing out to things that Luca said, that one of the motivations for the classical PCP theorem, what we already sort of knew that, there was this quest for hardness of approximation results, and this motivated classical PCP. And here, it's not clear that we have such a quest for quantum hardness of approximation results. So that does not motivate Quantum PCP. So I want to spend some time in the talk in trying to motivate quantum PCP on purely quantum information theoretic grounds, because I think now we have such grounds, and it makes the conjecture all the more interesting. It was interesting at the time. It's more interesting now. All right, go back to Scott. So this is Scott in his blog post, which is saying, well, okay, why haven't we solved this thing yet? And he's saying, well, one of the reasons is that no one has stated it formally, and it's true. I couldn't find a formal statement of the conjecture until after later. But he's kind of dodging the question. He's saying, well, let's just not worry about this, right? Quantum PCP theorem is anything that's interesting, and it's anything that's a robust version of the local Hamiltonian QUMA completeness theorem that I showed you before. All right, so the first formal statement of the PCP conjecture you can find, Umesh, this is the first I could find, so it's a paper by Aronov, Arad, Landau, and Vazirani, where they give two equivalent formulations of the conjecture, which are based on the two equivalent formulations of the classical PCP theorem that Luca gave us. So there's one formulation which is based on the concept of proof checking, proof verification. So the idea is that you should be able to verify this QMA witness, the state, by looking at only a constant number of qubits. And then there's another formulation which they phrase as a gap amplification problem. So the conjecture there would be that there exists a procedure which amplifies the gaps of these local Hamiltonians. You start with a local Hamiltonian instance that's QMA complete, has a promise gap that's inverse polynomial, and you want to map it to another instance where the promise gap now is a constant. So I'm going to give a statement of the conjecture which is neither of these two, but it's equivalent. So this is the local Hamiltonian, definition of local Hamiltonian. We saw this before. So here's the statement. We finally get to a statement of the conjecture. We've seen it many times before, but again, so what is the conjecture? It's saying that a particularly strong version of the local Hamiltonian problem is QMA hard. So it's saying that there exist two threshold values, A and B, that are separated by alpha. This is a parameter. Let's say think of alpha as a constant now, times m. M is the total number of constraints in the local Hamiltonian. So that an instance, so k is the locality, d is the dimension of the qubits. It's QMA hard to distinguish between these two cases. It's exactly the same as before. The only thing that's changed is that now before what we were asking B and A to be separated by an inverse polynomial, and now I'm asking them to be separated by a constant times the number of constraints. So it's a much stronger promise.
For every k and b.
Right, so I haven't been precise about the parameters, and as far as I know, there's no precise statement of the conjecture that makes any bets as to the parameters. So I want to spend some time discussing for which parameters this could be, for which parameters this is true, and which for parameters it could be true. We'd like to prove it. So for instance, I haven't said what alpha is. So if alpha is 1 over polynomial in n for a large enough polynomial, then we know this is true. This is the QMA hardness result I mentioned already.
Thomas?
Yeah.
Sorry. In the gap amplification version, it's not the same gap as in, right? It's a
No, let's not get into that debate. No, gap amplification it's the promise gap. It's this value, right? So it's not the gap of the Hamiltonian.
pointing out that we've used the word gap to mean
Yeah, sorry. So I don't know how you call this. This is the only gap I'll be talking about in this talk. No Hamiltonians will have gaps above the ground state energy. Okay, thanks. Okay, so let's stare a little bit at the parameters. So just because they're going to come up, this is the only parameters that are going to come up, but they'll come up over and over again, and I won't say always what they are. So n will always be the number of particles, the number of qubits. M, the number of constraints, and the number of constraints, the number of local terms will be polynomial in n. So I'll use n as my input size parameter. Okay, then there's k and d. So k is the locality, the number of particles on which each constraint acts. And for instance, if I allow k to be equal to n, then the conjecture is trivial. I'm not saying anything interesting because I can have just one term which is my original circuit, which acts on all the qubits. So what we'd like to have is, we'd like to prove this conjecture for constant k. But it's also interesting to think of super constant k. It doesn't need to be constant. For instance, polylogarithmic, k polylogarithmic in n is something that could be interesting. Same thing holds for d. So d is the local dimension. We'd like to get this for d constant. For instance, d equals 2, right? Just qubits, the basic case. But maybe, if it makes our life easier, it makes sense to look at slightly larger values of the local dimension. And finally, maybe the most important parameter is this promise gap. So let's call it promise gap instead of just gap. So as I mentioned, the conjecture is true for very small values of alpha. We'd like to get it for constant alpha. But as far as I know, again, it would be interesting to just get alpha slightly above, little o of these kinds of values. So 1 over polylog, or even 1 over root n, or something like this, depending exactly how you define it.
Can I ask, what is the best polynomial known?
Yeah, I don't know. Maybe Daniel knows. He said something the other day, but I'm not sure. 1 over n squared or n cubed.
L cubed is
N cubed, you're saying?
L cubed.
What's L?
The number of gates.
Oh, I see. So, and then...
M cubed.
Yeah, m cubed, I guess. I'm not sure, because when you translate the gates to the local Hamiltonian, you get more Hamiltonian terms than just the number of gates, because there's the clock and there's a lot of stuff. So, okay, I don't know.
I think there is a slightly better construction by Daniel Idar and forgot another one. Sorry. Yeah, by Aram Izel, where it's instead of having the number of gates, it's the depth of the circuit. So,
okay.
And then it's the depth of the circuit, I think, squared, right? Okay.
We don't really know. Let's take this for later. There's maybe some best result, but I don't know what it is, and it's at least 1 over n squared, let's say.
So this is even when k and d, you allow them to be poilog n?
I don't know. So allowing them to grow is barely looked at for all I know. So people really focus on k, up to 5 or something, and d can grow to like 10 or something like this. But so as far as I know, no one has really seriously investigated what you could say as soon as you allow them, or you start from the other side, right? You look at what if k is root n? Can you say anything interesting? But they would be sort of natural starting points or things to look at.
So one can also ask the other direction. For k equals 2, so for 2, 2, right, we know it's polynomial.
Yeah, right.
So which is not polynomial?
Yeah, so you can approach it by below, right. And I think 2, 2 is maybe the only case where it's... I was going to mention a few of these things in the next slide, so...
no, it's not... like even in the classical case, when k and d are 2, the problem can still be NP hard in this sense that there is a gap between completeness and soundness.
Yes. Yes, so we know that it cannot be QMA hard, I think, for 2, 2. So this for 2 and 2, even if alpha, I see.
There is this result of qubit and someone else.
I'm not sure. Yeah, I'm not sure. Let me see a few results I know, and then this one I'm not sure. So, okay, when is it true? There's very few cases where we know that it's true. We do know it's true if I get rid of QMA hard and put NP hard there. Luca discussed that. And we also know it's true if alpha is allowed to be inverse polynomial, so we've been over that before. And in that case, if you allow alpha to be so small, it's true with very strong parameters. So I'm stating some of these there. Okay, what are some limits that we know? And I'll get back to some of these limits towards the end of the talk, if we have time, so I can mention a few already. Okay, one case that's been looking at is if you restrict the Hamiltonians to commute, pairwise commute. This is interesting restriction because it makes the problem harder to work with, but it doesn't make it trivial at all. It doesn't reduce it to the classical case. But we do know that if you force the Hamiltonians to commute, and if the locality is 2, so the constraints act on 2 particles, or it's 3, but then you have to restrict the dimension to at most 3, or if the constraint graph has some good expansion properties, then the problem is in NP. And we also know, I guess Aram talked about this yesterday, that if locality is 2 and the constraint graph has a large enough degree, is Aram here? Am I messing up was it d squared?
Yeah, it's down to d squared now.
Okay, so I guess this is an old version of the result. I can never keep up. So if the constraint graph has too large a degree, then the conjecture is false for constant alpha. All right. That's, I think, basically the extent of what we know about the conjecture. So I'll talk about things we don't know.
And maybe you're going to talk about the power around Eldar result later, but...
Yes, which one?
Oh, just I would say that there's small set expander results.
Yeah, I was going to talk about it more.
Okay.
Well, sorry.
I just want to say it's only for very small sets.
Yes.
So it's actually barely
Constant size
stronger
sets,
condition
right?
than
Yeah.
degree one.
Okay, okay. Yeah, I'm not going to get into details of this. I think we won't have time. But there's essentially, for those who are interested, there's two sets of results that focus on how the graph, the constraint graph that maps, where which qubits the constraints act on, what are limitations on the kind of graphs that you could use. There's this paper that Aram told us about yesterday, and this paper by Aronoff and Eldar. They're good places to look at.
Can we just spend a couple of minutes? So somehow we do need expansion, but
right.
But very small set expansion is not good, and so. Can we sort of reconcile that? And
do we get to that later, or so I was going to get to it later.
At some point. Okay.
Yeah, it's clear that you need some expansion because otherwise you can chop up the graph into small pieces, right? So maybe we should have that discussion.
Other side, any intuition at all for the other side?
So Aram gave some in his talk. There's intuition related to monogamy. I mean, that's intuition for the degree. So the thing is. Right, so here we're treading the border between the problem between QMA hard or NP hard. And what this is saying is that your graph needs to be an expander in all cases, because if it's not an expander, basically it needs to have very good connectivity properties, because if it doesn't, then you can solve the problem just by chopping the graph into small pieces, solving it into each of the small pieces by some stupid brute force algorithm, and then just putting these pieces together. And if you've been able to separate the graph into small pieces by only cutting, there's only a few edges, so there's only a few constraints that you're ignoring by doing this chopping, then just putting the small pieces together will give you a good solution. Like it'll have energy which is not minimal, it'll be a little bit above minimal. And here we're allowing, a large margin, we're allowing to screw up a constant fraction of the constraints. So if you can disconnect the graph in small pieces by cutting a constant fraction of edges, this is not good. So it needs to have this kind of expansion, at least. These results are saying if it has too good expansion, or actually I'm not quite sure it's good to be saying if it has too good expansion, because you're right that this is a kind of very specific form of expansion, and the result here is mostly about the degree. So these results are mostly saying that the degree couldn't be too large, and here it's because if the degree is too large, then because of intuition related to monogamy, the ground state will actually be close to a tensor product state. In a tensor product state, you can represent classically using polynomially many bits, so that puts the problem in NP.
If I could push you further. So there's a somewhat similar story that's told in the UGC world, where sort of, but it's different. Yeah. So there, strong expanders are not going to be hard. But the story seems different, because there it's genuinely expansion and not degree. So can you illuminate this at all?
No, I mean, I cannot.
Yes, I'll say if you look at maybe max cut, it's a constraint satisfaction problem in a classical setting. If the graph has poor expansion at all scales, then you can get a sub-exponential algorithm for max cut by doing what you said. Cut the graph into pieces and solve locally. So the graph needs to have at least a kind of expansion to prevent an easy algorithm from existing in hard instances. But then if the graph has good expansion properties, or even small set expansion properties, then semi-definite programs do very well. So, so hard instances, even in the classical case, are those that are somewhat expanding but not too well expanding, and so that hard instances in general tend to look like.
I'm aware of that. I think the question is also, are there reasons that do this? So for instance, you pointed, the lower reason was the same. The upper reason is that SDPs do well. Can this be related to what I just said for why these instances would be easy in the quantum case, which is this monogamy? And I'm not sure they can, because here I'm not saying the instances, these are not cases where it's easy. It's cases where the problem is in NP, but it could still be NP hard. So, but
let me add, in our same paper, we also show SDPs do well on the quantum case, but when you not only have high degree, but also the same small set expansion properties that you do in the classical case. So, yeah.
So maybe it is quite.
Could be. Okay. I think this is an interesting discussion.
We could. This question for the hypercube.
So let's go on, and then maybe we have time to get back to it, and otherwise there's a long lunch break. It's an interesting question. So before going into probing like how you'd prove the conjecture, further obstructions than these ones, I wanted to do what I announced originally, which is to try to motivate this conjecture from a physical point of view, or try to see if it makes sense. Because there's a few sort of things that are in this statement here that might seem arbitrary, or it's not clear why we're making these choices. One kind of naive thing is why do we look at the minimal energy or the ground state? More interesting thing is why are we really interested in proving QMA hardness? We have NP hardness already, and isn't that hard enough? I mean, what's the difference between hard and very hard? Okay, a smaller question is why do we really want K and D to be constants? It's an easy question. Again, a harder question. Why do we want this constant gap alpha? What's the significance of that? Right? Aren't we happy with? I mean, what's this gap saying anything? So, and the answer hopefully is related to the physical motivation for the conjecture. So I'll try to not spend too much time on this, but spend a little bit of time over all of these 4 questions, give you some motivation. If there's some physicists in the audience, I hope there is not. Okay, good. Especially now. So why the energy? I don't know. It seems to me that energy is just a fundamental quantity that you can associate to most physical or all physical systems, and it kind of acts as a represents. It's a simple thing that you'd want to know about any system that you can measure in the lab, depending on the system. There's many different ways you could measure the energy, and it just serves as a proxy for interesting property of my system or basic property of my system. So why the minimal energy? Well, that's the energy of the ground state. So why the ground state? So there's been a lot of discussion already about this. I want to just make the discussion a tiny bit more precise. So one thing that we know is that when you have this local Hamiltonian, which describes the constraints on your system, and the system is at a certain temperature, then the equilibrium state is given by this Gibbs-Boltzmann distribution. So the state will be, this is the density matrix of the state, and it will be proportional to exponential in minus. So this is just a constant divided by temperature times the Hamiltonian. So this means that your state will be such that eigenstates of the Hamiltonian that have a certain eigenvalue, E, any eigenvalue, has probability of arising at a certain temperature that is proportional to this thing here. So if you look at the plot of this function, so this is that function for different temperatures, and as the temperature gets smaller, the probability function goes, to the left, and it becomes more pointed. Which means that as the temperature goes to 0, this stationary distribution, the equilibrium of your system, this becomes concentrated on eigenstates of the Hamiltonian, which have small energy. Okay, so the sort of conclusion of this is that what's the ground state? It's the steady state, the state of equilibrium of your system when the temperature is 0. So why are we interested in 0 temperature? I know most systems are not at 0 temperature, but the systems that you can work with in the lab tend to have 0 temperature. That's when they're stable. So that's when you can do measurements, experiments, you can control the properties of the material. So it's kind of relevant to be looking at the most stable states of your system. These are those that you can control the best. But they're not necessarily the most relevant either. For instance, it's not necessarily the case, and we'll talk about this a little bit more later, that these states exist. So you can try to cool down your system, make it reach the ground state, but it might not happen. You might not be able to get a system that's stable. So the conclusion of this is that ground state kind of makes sense, but it's also a little bit arbitrary. I mean, there's many other states that are interesting. Here we focus on the ground state because we have to start somewhere, and it seems like it's the thing that you can understand, and that's interesting.
Yeah. I don't know too much physics, but what's the relationship between the temperature, which I understand is some average quantity, is some average measure of energy, and the energy eigenvalue of certain eigenstates?
No, so the temperature is just the temperature you measure using the thermometer, and the energy is all kinds of things like kinetic energy, potential energy. chemical.
Can I answer to this question? Because
Sure.
I just looked at this formula and I all of a sudden got enlightened.
So we'll get back.
So I looked at this e to the whatever kb divided by t times h, and so that's not you, and you said that's a density matrix, but that's not a one-dimensional density. I mean, that's not a rank 1 density matrix.
No, it's right.
So it is a mixture of various states. So what it says is that at temperature T, this is the mixture. And I think that was just very enlightening for me, that it is not a single eigenstate, but it is a certain mixture, and if you change the T, then it's just going to be a different...
Yeah, so that's the point of this picture. As T goes to 0, your mixture becomes more and more concentrated on just a single point, which is the ground state.
And the temperature is just, I mean, my basic knowledge is, temperature is like sort of the average velocity of the particles in your system.
So that's maybe a little too special. I mean, that's fine for gas particles in the room or something, but somewhat more generally, the temperature expresses the rate of change of the entropy with respect to energy. So if you were to put a little more energy into the system, how many more states could the system occupy? So that rate of change is expressed by the temperature.
So the K and D parameters I'm not going to spend time on. These, it's natural to require them to be constants, at least the locality, because these Hamiltonians, the number of qubits on which they act on, these Hamiltonians are modeling forces that act on the system, and I think Daniel or this, we talked about this before. The models of physics that we have talk about 2 local or 3 local interactions. We don't typically have interactions that involve too many particles. The laws of physics are like this, right? There basically be attraction or repulsion forces between neighboring electrons or things like that. The dimension, you could argue a little bit about it, because depending on your system, how it's modeled, you could think of a system that has continuous degrees of freedom, in which case you could be asking, well, what if I allow D to go to infinity? But D here is also a measure of how complex these constraints can be. So Hi acts on these, let's say k equals 2, so it acts on these 2 particles, each of which has dimension D. If I allow D to be very large, I'm allowing my Hi terms to be very, very complex, and this is kind of putting the complexity in a place I don't want it to be. So I think it's natural to require D to be a constant or something that grows slowly. But maybe there's other parameters that are not part of the conjecture, but that would make sense physically. Which is that, typically these Hamiltonians, which describe the constraints of your system, they tend to be not only local in the sense that they act on a constant number of particles at a time, but also they only act on neighboring particles, right? And it's neighboring in the sense that your particles are arranged maybe on a 2D or on a 3D lattice. Another thing that tends to happen is that each of these local terms here should be the same, essentially. So there should be some translation invariance. For instance, if Hi is supposed to model a repulsive force, this repulsive force is the same in between any 2 pair of electrons, whether they're here or they're over there. This is something that's not required as part of the conjecture in the way that I stated it, but it's a desirable property, that the Hi's would all be the same or very close to being the same, up to maybe some weights. And in terms of QMA hardness, so if I allow the gap to be small, then in recent years, even this year, last year, there's results on this, and I mentioned this already, they come close to achieving QMA hardness for these kinds of physically relevant systems. All right, more interesting question. So why are we interested in showing QMA hardness instead of NP hardness? What's the physical relevance of making a statement that local Hamiltonian problem is QMA hard for constant gaps instead of just being NP hard for constant gaps, which is something that we know already from the PCP theorem. So the difference between the two is that we're saying that, well, the problem is not in NP, right? That's one way to think. I mean, if we assume QMA is different from NP, or we're even saying that, okay, the problem is not in QCMA, so this is saying that there is no classical witness, right? That's what kind of, I think, morally what we want to say when we're saying QMA hardness. and not beyond NP hardness, we're saying that there is no classical witness. There is a quantum witness for my system having low energy, but no classical witness. And what this is saying is that if there is no classical witness for the fact that my Hamiltonian has a very low energy, it means a few things. I mean, first, it means that there is no classical witness for the fact that the ground state has low energy. In particular, there is no efficient classical description of the ground state that lets me compute its energy from it. So for instance, the ground state cannot be a tensor product state. If it was, I would have a classical description. So it must have high enough entanglement. High enough entanglement, okay, another thing, for instance, is that the ground state cannot be generated by, actually, polysize, this is wrong. I should have written by a log depth circuit. Because if the ground state could be generated from a product state by a small depth circuit, I could give that circuit as my classical witness, and you can verify that this circuit would let you compute the energy in polynomial time. So that's a form of saying, this is going back to Aram's question. Aram, I have a suggestion. I was going to get back to this later, but I don't know. So in Aram's talk, he was saying, the only obstructions we have to QPCP are cases where we can say that the ground state is well approximated, in some sense, by a tensor product state. And then he was saying, well, we want to go beyond that and think of cases where we derive obstructions by saying, well, the ground state is maybe not close to a tensor product state, but it's close to something that's slightly entangled. And then we have this whole wealth of entanglement measures to choose from, and we don't quite know how to measure slightly entangled. So that's a very natural way to measure slightly entangled in terms of the QPCP conjecture. We can say that the state is a little bit entangled if you can generate it from a tensor product state via a low depth circuit. So that would be, yeah.
Sorry, can't you use a polysize generating circuit?
No, so that would give you a classical witness, but it's not clear you would be able to compute the energy. Because a polynomial size circuit can generate a lot of entanglement, so you wouldn't be able to contract the tensor network.
Wouldn't it show that it's QCMA? It's in QCMA?
Yeah, QCMA. Yeah.
So that probably means that it's not QMA hard, right?
No. Oh, that's it. Yes, yes, sorry, yes. Okay, okay, yes. Okay. Another point here is that, right, so I guess this relates to your question, which is to say, you know, in trying to put the problem in NP, it's not clear what the classical witness for the state should be. So for instance, you can think of a two-dimensional state that would have a two-dimensional tensor network representation. So that's something that I can specify efficiently classically, but doesn't allow me to compute the energy. So it could be that the conjecture is true, that ground states have efficient classical descriptions, but you can't efficiently compute the energy or verify that the energy is low from these descriptions. This is a type of description for which I don't know if you can compute the energy. Another interesting point also is that if you try to prove the problem in NP, it's not clear that the witness needs to be a representation of the ground state itself. It needs to be something that convinces you that the energy is low. And we have one example of this that we came up with. I mean, it's very simple, but in the survey with Dorit and Itai, so is to show that QMA, so the local Hamiltonian problem, has exponential size classical witnesses. So if you try to put the problem in NP, you want a polynomial size description of your state or polynomial size witness. What we can show is that there's an exponential size witness, but that you can verify just by making a constant number of queries. So this is saying that there's a way to encode your quantum state into exponentially many bits, which is so far trivial because you can just write all the coefficients. But this encoding has the property that you can evaluate or verify that this state has low energy with respect to your Hamiltonian just by looking at a constant number of entries, so a constant number of coefficients. The fact that this kind of proof exists actually follows from very known things, from the fact that QMA is in p-space is equal to IP, etc. It follows from the literature. But just writing it explicitly is interesting. And this proof has a property that it does not encode the state itself. It encodes properties of the Hamiltonian directly. And just by looking at the witness, you can make the verification without having any idea what the state is.
Although that just means that QMA I mean, that exponential size classical proof, it means it's nx, right? And did not we know that?
Yes, of course.
That QMA is in nx.
Yes, yes. So, so it says a little bit more because you can verify it locally, but of course we know that nx is equal to, I don't know, MIP. So you can verify if you know the PCP theorem. So yes, we knew this. Yeah. Yes, I'm not claiming it as a result. Sorry, I was just, the result is just to sort of, instead of saying what you said and then having to figure out what is the proof by doing a lot of reductions and having all kind of error correcting codes and all kinds of things, we have just a like one paragraph proof which says exactly what is this proof looking like and relating it to the local Hamiltonian. It's kind of a very natural proof. So, but there's nothing new. It's an exercise. You can do it. It's an interesting exercise. This is what I wanted to say. Okay, one last thing is why do we want constant gap? Why is that relevant? So this brings us back to this Gibbs distribution. So the reason the constant gap is going to be relevant is so that you make statements not only about the ground state, but about states that are above the ground state, so about excited state. So this Gibbs distribution, if you look at it, this density matrix here is a distribution on eigenstates of the Hamiltonian, and it's a distribution which is going to be concentrated on states that have energy that go up to n times temperature over kb, right? Because above this, then the probability becomes exponentially small. So even though there's exponentially many states, the contribution to the total probability mass will be very small. So now, the PCP conjecture is saying that it's hard to make the difference between the ground state energy being something and the ground state energy being alpha times m or times n. Let's think of them as being the same above that. So it's not only saying that there is not a classical witness for the ground state, it's saying that, you know, if your energy is very low, but the problem is not in NP, there's not a classical witness for any state that has energy the bottom, the A parameter, and also very far above, up to until you reach B. So there's no witness for any of these states. Any of the states that have energy between A and A plus the gap, roughly. And because the gap is alpha n, you're saying that there's no classical witness for all the states that show up in this distribution as long as the temperature is at most Boltzmann constant or something times your gap. So this is what it's saying. Not only the ground state must have high entanglement, but all states that have low energy must have high entanglement, because otherwise they could also be fine witnesses. You don't need to provide the ground state as a witness. You need to provide anything that has energy less than the B parameter, and that's fine. That's because of the promise, it's enough to certify the ground state energy is small. And these are the states, because of this formula here, these are the states that arise at temperatures that go up to constant temperature. So these are much more sort of realistic temperatures. So that's one very strong statement Quantum PCP is making. Not only the ground state is very entangled, which is something we might believe, but also that many states that exist at higher temperatures, also these should also be highly entangled. Otherwise, we could give them as witnesses. And this, it depends who you talk to, but it might run to some counterintuition. Like physicists might say that, no, but look, I mean, at high temperature, or high temperature, I mean, not necessarily that high, right? It could be 10 Kelvin or 100 Kelvin or something like this. But things become much more disordered, like the system becomes more complicated, and it's unclear whether you can have entanglement at that temperature. It's one of the things that make quantum computers hard to construct, right? You have to make these fridges to keep things stable, to control your entanglement.
But those would also be states that are difficult to construct, because otherwise
Which states? Sorry.
The ones that come from these hypothetical
quantum computers.
Theorem.
Oh, yes.
Yes.
Somewhat
simple states, then
of course, right.
It would not be the QMA hard states.
Yeah, right.
So this would say that it is possible to that there are states that stay entangled at very high temperature, but they're sort of physically unrealizable because the complexity of building them.
Right, exactly. So that's kind of the tension between the conjecture, because on the one hand we're saying there's physics, that there's things that exist that we can control in the lab, that, and surely these cannot be QMA hard because we can construct them and manipulate them, and they've existed and they've been built in, a few years or a few million years or whatever since the Earth exists. So these cannot be QMA hard, right? And on the other hand, we're having this conjecture and we're trying to say, look, these model real systems because it's a local Hamiltonian, because etc. And I'm going to try to prove that it's QMA hard. And there's this tension between the two. And so I guess parts of the conjecture,
So another way of saying it is these are systems which couldn't be cooled, or it's the quantum analog of spin glasses.
Right. Right. So that's this thing here. Yeah.
But that's not the only possibility. There's also sort of the ICE-9 possibility.
The what? The what?
ICE-9 is something where if you have one copy of it, you can create many more cheaply. So the first copy is hard to create. So this is also within, this is compatible with quantum PCP being true.
So that's like the advice version of.
Yeah, but even.
But how did you create the first state?
Well, maybe that's been around for a billion years.
I see.
I'm not saying that's a good idea, but I'm just saying that it's, there's a lot of room within these conjectures.
Maybe, actually, just to clarify your little warning content there, entanglement not persisting at room temperatures, now we're talking about a particular Gibbs distribution, is not, I'm quite sure that, so when we talk about the Gibbs state,
you mean even this one doesn't exist, or doesn't necessarily? It's true in a way. The Gibbs is the equilibrium state, but you might not be in equilibrium.
Yeah, it's quite different. Actually, or at least I'm not seeing the equivalence between sort of proofs of the existence of a single state below some threshold energy versus whatever physicist's intuition is about entanglement in in Gibbs states.
I agree. I don't really know. You're right. Also, this is a mixture over many states, and it could be that each of these states individually has high entanglement, but when you have the mixture, you don't see any of it. Or,
I'm not clear on that, on what can happen.
Except once you have a mixture, wouldn't you sort of say that so how close to entanglement it is depends upon, you write it as an equivalent mixture and so on.
But I mean, you can. Right, I mean, you can have mixtures of very entangled things that have no entanglement, right? Yeah. Like the totally mixed state is a mixture of everything, but it has no entanglement. So, yeah.
That was exactly my point, that those two things that don't seem to be counter to one another.
Okay, so good. One less roadblock. No worries, we have a lot of others. So,
So about the physical interpretation of this about entanglement of state, would you agree that for a particular Hamiltonian that you might be interested, that the ground state could be totally unentangled? I mean, from this, I guess we can conclude that in that class of Hamiltonians, there are many ground states which are highly entangled. But if you're interested, I mean, because I guess that's what you're even more interested in for a physical problem, that if this given Hamiltonian is entangled or not, this doesn't tell you anything.
Yes, I think what you're saying maybe is that here we're really studying worst case complexity. So even if the conjecture was true, it would be saying that there is a Hamiltonian in this particular class that has these properties of having highly entangled. But of course, it might not be the Hamiltonian that arises. So, but that's a little bit of the work that's done. I mean, it's always still worst case, but in the QMA hardness results that I mentioned before, so that don't have this promise on the gap, this is what people are trying to do when they're saying, okay, we're trying to show QMA hardness for two local systems on the grid or translation invariant, and so you put more and more constraints to try to get closer and closer to the kind of systems that are relevant. But even then, right, it's a worst case thing, and it might not be the one that's in your lab. Yeah.
But it also informs the intuition, right? Because before the QMA hardness results, the intuition was that 1D systems are easy no matter what. It really helps.
Right, that's true. Right. Yeah, that's a good point. I mean, I guess same thing with this, right? I mean, there's a lot of intuition in physics as to how systems behave. And maybe here we're just trying to sort of push that intuition around and see where it extends. I mean, right. I think this is relevant also in these the algorithm that Zev told us about, this one-dimensional algorithm, polynomial time algorithm that relies on the existence of a spectral gap for the Hamiltonian. So in this kind of situation, there might be some intuition, some physics intuition that says, well, like Umesh was saying, 1D systems are easy. Okay. Then we'd be asking, what do you mean by 1D system? What's the property of a 1D system? And you'll say, well, it's a 1D system. The constraints are in one dimension. And then people work, and then they come up with a QMA hardness result for what you were saying. And then you say, well, how come you have a QMA hardness result, and you're telling me they're easy? Then we have to look at it a little bit more, and then you realize, but all the systems that actually arise in my lab have a spectral gap. Maybe that was the reason why it was easy, not necessarily 1D, it was a spectral gap. And then we'd work on the other side, or Zev would work on the other side and say, well, yeah, okay, now you tell me spectral gap, now I have an algorithm. So it's also kind of a way to sort of unearth what are the important properties from complexity point of view.
That's a completely stupid question. So are we talking about positive instances or negative instances? Because, so when we are discussing this entangled ground state, or are we talking about both? Positive instances are...
positive instances. I mean, a witness for a positive instance. To have a witness for a positive instance needs to be something that convinces me that there is some state that has kind of low energy, right? So these are the instances. I think so, mostly, yeah.
And the negative instances are not a question, or are not special or something. But in any case,
I mean,
this discussion is about positive.
Right, okay, yeah, right.
Okay. Sorry.
Yeah, I guess, yeah. But by definition of...
That those interesting properties, so those exist only for quantum.
Okay.
So we're done with part one, and time's up. So maybe I'll steal 2 minutes, try to say, now, there was a discussion of approaches based on what Luca told us, 2 different proofs of classical PCP theorem. We have these proofs, why don't we try to adapt them and see what goes wrong? So I had sort of things that go wrong in both of these proofs, but maybe I'll just say one thing that goes wrong, and then, then we should.
Can I suggest we go a little longer?
But that will be already 5 minutes, and if there's questions. Yeah, the afternoon also is very strict. So, but 5 minutes is okay, or I could also just okay. So I'll just do 2 slides. The first slide is Scott telling us what's the way to go. So back to his blog. He's saying exactly what I just said right now, right? If you want to prove the quantum PCP theorem, then just look at the classical proofs, and these involved a lot of steps. They required a lot of work. Let's get inspiration from these steps. And he's also already pointing us to the difficulties. He said, so at the time, Reed's proof was very new, I think. So people were very excited by it, and he spent 1 day studying it. So Scott is fast. But in 1 day, he already found a lot of obstructions, so violations of no cloning theorem. So this, which is not something I'm going to get into in my one remaining slide. So I guess. So let's see. This one, so the original proof of the PCP theorem, Luca mentioned, involves a lot of work using error correcting codes. And the error correcting codes that go into the proof there's different types of them. They have 2 important properties. One is that they're locally decodable, and the other is that they're locally testable. I'm going to focus on just this one property. So local decodability of a code, of an error correcting code, means that you encode your word into a code word. It has the property that if you just want to recover not the whole original word, but just a single coordinate, you can do this by reading few bits of the encoding. I put polylog here, but ideally it's better than that. It's just a constant number of bits of the encoding. These play an important role because they let you sort of recover information about the original assignment just by making a few queries to the proof. So one of the natural things to do in trying to prove this quantum PCP is try to see if we can come up with quantum locally decodable codes. And there's a rich theory of quantum error correcting codes, definitely, and we'll hear about that later. So it makes sense to look into that and try to get this property. I'm not quite telling you why we want this property, but we're out of time. I just want one slide to argue that we cannot have such a thing in the quantum regime, not at all. Right, so let's see why, right? So suppose we had a quantum error correcting code. It encodes, a bunch of qubits. X here is just a basis state, classical string, and X bar is the encoding. So it's just how I encoded my state. And suppose that this code has a distance at most k, which means that any kind of error that I make that acts on k qubits at most, I can correct in a certain way. Suppose this code was locally decodable. So suppose I have some procedure, di, so it depends on I. This is the coordinate I want to recover, such that when I run this procedure on the encoded word and this some ancilla, I can recover I can decode this coordinate here. All right?
Without destroying the code.
Without destroying the code word. This is where the problem is going to arise. So presumably you don't want to destroy it because this is your witness, and you might be making more than one query. So this is... sorry?
That's cloning.
Yeah, you're right. Yeah, the way... I see. So, right, the way I wrote it is a bit silly because it implies cloning if you... So, this X could be a classical string, in which case it doesn't imply cloning. But you're right.
So why couldn't you have many copies of it to begin with? So why can't you destroy? So in your quantum PCP theorem, you start with some classical description. Yeah. You can make as many copies of anything that you want.
Yes.
Whatever procedure you have, and then each time you make a query, you make it to a different copy.
So it's fine to destroy it, you're saying?
Yeah.
Okay. So I guess my slide is only going to argue that quantum locally decodable codes must destroy the whole code word in order to recover just a little bit of information.
Well, it's not.
But that's a good point.
When you want self-consistency, right? Even within each copy, I mean, what if the adversary makes a different kind of?
Can't you do swap tests? Oh, I see, but that's too many queries. I see.
Could you ask for just some part of the thing to be, so you can't recover? I mean, isn't it reasonable to say something like you've got some piece of the code word left that you can use without?
Yeah, I guess so. So you could, so maybe this is a weak limitation I'm giving to you. So it's in the section of approaches, not in the section of obstructions. So it's just okay. I guess it's just one thing you need to keep in mind, and there's probably ways to get around it, but at least this is something that would be straightforward classically and is not in the quantum case. Let's put it to that. Okay, so then I just wrote Y here because if you could do this coherently, then you could start from the encoding of a superposition. So here I encoded a superposition of two inputs, one in which the ith bit is 0 and the other in which the ith bit is 1. And so when I run the local decoding in superposition, which is supposed to be a unitary, it's a quantum procedure, then this decodes a 0 and this decodes a 1. And if I throw these bits that I just decoded away, what I end up is with a mixture of my two original code words instead of a superposition. So what we have here is that we have this procedure, the decoder, and the decoder is a procedure which is local, so it acts on at most k qubits. But by running it and then discarding the outcome of the procedure, I've destroyed the original superposition that I had. This is a simple superposition of two states. So this is a contradiction with the distance of the code being less than k. Distance of the code being less than k means that you should stay, it should be possible to correct this. And here I screwed up the superposition, so I'm not able to recover my original words from this. This is irrevocably lost. I agree. It's maybe I shouldn't have written this in red. It's let's ignore those. Okay, so that was just one thing. There's also obstructions more seriously researched obstructions on local testability that I'm not getting into. And there's also... Sorry?
Minus 10 minutes.
Yes, so I'm stopping right now. There's also work in extending Irit's proof, the gap amplification proof, and there's also by Umesh and others, and there's also obstructions there. And I'll stop at minus 10 minutes. Okay, fine. Yeah, thanks.